The universe recycles its dead to create new life across cosmic time. Galactic graveyards are where this extraordinary rebirth happens, vast regions where the remains of ancient stars become the raw materials for future worlds. By the end of our journey, you will see the night sky not as a static picture, but as a living, breathing cycle of creation. How did the iron in your blood once power a star that died billions of years ago? And what cosmic alchemy forges gold in stellar explosions? What part of this grand cycle of death and rebirth resonates most deeply with you? That brilliant starlight we admire is the visible fire of a star's internal engine. Deep within its core, an immense pressure squeezes atoms of hydrogen together so tightly that they fuse, creating helium and releasing a torrent of energy. This process, nuclear fusion, is what makes a star shine. It is a constant battle, a precarious balance between the inward crush of gravity and the outward push of radiant energy. For most of its life, a star maintains this equilibrium, burning steadily for millions or even billions of years. But like any fire, it cannot burn forever. The fuel will eventually run out. What happens next is one of the most defining moments in a star's existence, and its fate rests entirely on a single characteristic: its mass. Think of a star's mass as its destiny. A relatively small star, like our own Sun, has a long, stable life and a relatively gentle end. After it exhausts its hydrogen fuel, it swells into a red giant, eventually shedding its outer layers into space. This creates a beautiful, glowing shell of gas and dust known as a planetary nebula, while the star's core remains as a white dwarf, a hot, dense ember that slowly cools over eons. But for stars born with several times the mass of our Sun, the story ends with far more drama. Their immense gravity creates such extreme conditions in their cores that they can forge heavier and heavier elements, all the way up to iron. And iron is the ash that chokes the fire of fusion. When the core can no longer support itself against its own weight, it collapses in a fraction of a second. This collapse triggers a cataclysmic rebound, a supernova explosion so powerful it can, for a brief moment, outshine an entire galaxy. It is in these violent, final moments that the universe forges the elements that make up our world and us. The calcium in your bones, the oxygen you breathe, and the iron in your blood were all created in the heart of a star that lived and died long before our Sun was even born. This cycle of stellar life and death is the universe's greatest recycling program. Each ending is also a beginning, scattering the raw materials for new stars, new planets, and perhaps new life across the cosmos. But these cosmic graveyards are far more than just quiet resting places. Picture the aftermath of a supernova, a vast and chaotic cloud expanding at millions of miles per hour. This is a supernova remnant, a churning cauldron of gas and dust that is anything but peaceful. Within its turbulent heart, titanic shock waves race outward, acting like cosmic snowplows. They sweep up the thin material between the stars, compressing it into incredibly dense knots and filaments. It is in these intense pressure cookers that new stars can begin to coalesce, born directly from the ashes of the old. Meanwhile, the more gentle end of a star like our Sun creates a different kind of structure, a planetary nebula. Despite the name, these have nothing to do with planets. They are the beautiful, intricate shells of glowing gas, the final breath of a star shed over thousands of years. Their ethereal glow comes from the fierce, ultraviolet radiation of the hot stellar core left behind, which energizes the expelled gases, making them shine in brilliant, otherworldly colors. So to call these places mere graveyards is a profound understatement. They are dynamic factories and nurseries. The complex physics at play, from searing radiation to crushing shock waves, tirelessly work to forge and redistribute the elements essential for creation. Every oxygen atom you breathe and every particle of carbon that forms the basis of life was likely processed through such a region. These are the galactic recycling centers, without which new solar systems, rocky planets, and the chemistry of life itself would simply not be possible. The death of a massive star is a violent and spectacular finale. When its core can no longer withstand its own immense gravity, it collapses inward and rebounds in an earth-shattering supernova explosion. For a few brief weeks, this single event can shine brighter than every other star in its galaxy combined. But the story does not end with that brilliant flash. The true legacy of the explosion unfolds in the expanding shell of debris it leaves behind, a structure known as a supernova remnant. This colossal cloud, composed of searing hot gas and dust, races outward at thousands of kilometers every second, carrying with it the very elements forged in the star's final moments. The Crab Nebula is a stunning example, a tangled web of glowing filaments that is the scattered remains of a star observed to explode on Earth in the year 1054. Within such chaotic remnants, the intense heat and pressure of the blast act as a cosmic forge, creating heavy elements like iron, gold, and even uranium. These newly minted atoms are then violently ejected, seeding the surrounding space with the building blocks for future planets and, potentially, life. Yet the remnants' work is not merely distributive. Its leading edge, a powerful shock wave, slams into the quiet clouds of gas that drift between the stars. This cosmic snowplow compresses the material, creating dense pockets where gravity can finally take hold and pull together the ingredients for a new generation of stars. This is the ultimate cosmic feedback loop, where a single, catastrophic stellar death directly triggers the birth of countless new suns. While a supernova is a violent cosmic detonation, the end of a star like our Sun is more like a serene and prolonged farewell. In its final act, a sun-like star does not explode. Instead, it gently exhales its atmosphere into the void, creating one of the most beautiful sights in the universe, a planetary nebula. These are not the remains of planets, but rather the final, glowing breath of a star, a luminous shroud of gas illuminated by the intensely hot core left behind. That core, having shed its outer layers, becomes a white dwarf, a stellar ember that will slowly cool for billions of years. The intricate shapes of these nebulae, from the delicate rings of the Ring Nebula to the vast, eye-like structure of the Helix Nebula, are sculpted by the complex dance of stellar winds and radiation pressure. This process is a masterclass in cosmic artistry, where forces we can barely comprehend paint ephemeral masterpieces on a canvas light years across. And within these beautiful clouds lies a profound contribution to the galaxy's future. The expelled gases are rich with newly forged elements like carbon, nitrogen, and oxygen. These are the fundamental ingredients of organic chemistry, the very stuff of life itself. So while this stellar passing is quiet, its legacy is immense. It gently seeds the interstellar environment with the essential building blocks for future planets, oceans, and perhaps one day living organisms. This demonstrates that cosmic renewal does not always require a cataclysm. Sometimes, the most significant contributions come from a graceful and gentle exit. And so the beautiful glow of a planetary nebula fades, leaving behind its hidden treasure. The star's core, no longer fueled by fusion, endures as a white dwarf. This is what remains after a star like our Sun completes its long life. Though it contains the mass of a star, This core has collapsed into a sphere roughly the size of our own planet Earth. The result is matter of almost unimaginable density. A single teaspoon of white dwarf material, if you could bring it to Earth, would weigh as much as an elephant. This incredible compactness is not held up by the fires of fusion, but by a bizarre quantum mechanical effect. The electrons within the star's core are squeezed so tightly together that they push back with a fundamental force, creating a final, permanent resistance against the crush of gravity. A white dwarf is a stellar ember, a fading cinder of carbon and oxygen that will slowly cool over many billions of years. It represents the final state for the vast majority of stars in our galaxy, a quiet and enduring monument to a life once lived in brilliant light. Yet even in this dormant state, a white dwarf can hold the potential for sudden, violent rebirth. In a binary star system, a white dwarf can have a stellar companion. If these two stars are close enough, the white dwarf's powerful gravity can begin to siphon hydrogen-rich gas from its partner. This stolen material accumulates on the white dwarf's incredibly hot surface. Over time, the pressure and heat build until they trigger a runaway thermonuclear explosion. This event, called a nova, can cause the star to flare brightly for a short time, outshining its normal luminosity by thousands of times. It is a spectacular, recurring eruption that does not destroy the white dwarf itself. In some rare and critical cases, however, the white dwarf can pull over so much material that it pushes itself over a precise mass limit. This triggers a far more violent and complete detonation, a Type 1, a supernova. This titanic explosion is so powerful and so uniform in its brightness that astronomers use it as a standard candle to measure vast distances across the universe. These cosmic yardsticks helped reveal the shocking discovery that the expansion of our universe is accelerating, a finding that earned a Nobel Prize. So from a quiet, fading ember comes a tool that allows us to measure the cosmos itself and to uncover its most profound secrets. But the stellar afterlife holds forms even more extreme than the white dwarf. When a truly massive star explodes, its core does not settle into a quiet, electron-supported state. Instead, the collapse is so violent and complete that it forges one of the most bizarre objects in the cosmos, a neutron star. Picture the entire mass of our Sun, or even more, crushed into a perfect sphere no wider than a city. This is matter pushed to its absolute breaking point. The immense gravitational force of the collapse is so overwhelming that it fuses protons and electrons together, creating a solid ball of neutrons. The density is almost beyond comprehension. A single sugar cube's worth of this material would weigh as much as an entire mountain here on Earth. These are the universe's ultimate density laboratories, places where the rules of physics are stretched to their absolute limit. Some of these neutron stars reveal themselves through a spectacular cosmic display. As they are born from the chaotic collapse of a star, they often begin spinning at a dizzying rate, rotating hundreds of times every single second. Their unimaginably powerful magnetic fields, trillions of times stronger than Earth's, funnel intense beams of radiation out from their magnetic poles. If one of these beams happens to sweep across our line of sight as the star rotates, we observe a regular, repeating pulse of energy. We call these objects pulsars, the lighthouses of the galaxy. Their rhythmic flashes are so precise that they rival atomic clocks, providing astronomers with some of the most reliable timing signals in the universe. Yet the most profound role of neutron stars is not in their steady pulses, but in their catastrophic collisions. When two neutron stars in a binary system spiral inward over billions of years and finally merge, the resulting cataclysm is one of the most energetic events since the Big Bang. It is in these violent collisions that the universe forges the heaviest elements. The intense conditions create a cosmic crucible where gold, platinum, and other precious metals are born. A single merger can fling outward enormous clouds of this newly forged material, seeding surrounding gas clouds with the stardust that will one day coalesce into rocky planets. The gold in a wedding ring or the platinum in a catalytic converter was likely created in such a spectacular collision, an event that occurred long before our own solar system even existed. These incredible objects born from death thus become the ultimate creators, responsible for sprinkling the galaxy with the very elements that make advanced worlds and perhaps life itself possible. Yet even the incredible density of a neutron star is not the final chapter. For the very largest stars, gravity achieves its ultimate and most absolute victory. When the collapsing core of a dying star is too massive to be stabilized by the quantum pressure of neutrons, nothing in the known universe can stop its descent into oblivion. It collapses into a stellar mass black hole, a region of space where gravity is so intense that nothing, not even a single particle of light, can ever escape. This is the point where the familiar laws of physics as we understand them cease to apply. The boundary marking this point of no return is called the event horizon, a one-way membrane shrouding the incomprehensible singularity at its center. While these black holes are often imagined as cosmic vacuum cleaners, their true role is far more nuanced. They do not directly contribute their own material to new stars, for that matter is locked away forever. Instead, they act as gravitational architects, a stellar mass black hole moving through a vast cloud of interstellar gas can exert a powerful tidal force, compressing the material around it. This gravitational squeezing can initiate the collapse of dense pockets within the cloud, effectively triggering the birth of new stars in its vicinity. Furthermore, material drawn toward a black hole does not fall straight in. It forms a rapidly spinning, superheated structure known as an accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to glow with intense X-rays and other high-energy radiation. This radiation can blast surrounding nebulae, influencing their chemistry and potentially driving complex reactions in the gas that will one day form new planetary systems. So while a black hole itself is a tomb from which nothing returns, its immense gravitational presence and energetic output can sculpt the space around it, fostering the very conditions necessary for new creation to begin. They are the darkest of graves, yet paradoxically, they can also become cradles. This vast cosmic recycling system depends on a seemingly empty stage. Drifting between the stars is a faint, pervasive mist known as the Interstellar Medium. It is the ultimate raw material, the primordial canvas upon which the entire cycle of stellar death and rebirth is painted. This medium is not a true vacuum, but a delicate mixture of gas and dust, so thin that the best laboratory vacuums on Earth seem dense by comparison. Its composition is a testament to the universe's history, made mostly of pristine hydrogen and helium left over from the Big Bang. Yet scattered within this primordial gas are traces of everything else, what astronomers simply call metals. Every atom of carbon, oxygen, silicon, and iron is a piece of stardust, a direct contribution from a long-dead star. The character of this interstellar medium changes dramatically from one region of a galaxy to another. In some places, it collects into immense, cold, and dark molecular clouds. These are the deep freezes of the galaxy, where temperatures hover just a dozen degrees above absolute zero. It is within these frigid, dense nurseries that gravity can finally overcome pressure and begin to pull new stars together. In stark contrast surrounding brilliant, Hot stars are vast regions of the interstellar medium that have been heated to millions of degrees and ionized by intense ultraviolet radiation. These bubbles of searing plasma are the active construction zones, churned and shaped by the very stars they helped create. This is where the stellar graveyards perform their most vital work. When a supernova remnant expands or a planetary nebula dissipates, it does not simply vanish. It injects its newly forged elements directly into this surrounding canvas. This process, called chemical enrichment, is how the galaxy grows up. The first stars to form after the Big Bang were made of only hydrogen and helium. They lived fast, died young, and in their spectacular deaths, they polluted the pristine interstellar medium with the first heavy elements. The next generation of stars formed from this slightly enriched material, and when they died, they added even more metals. Over billions of years, with each successive stellar generation, the interstellar medium has become richer and more complex. Our own Sun is a product of this long history, a star formed from gas that had been cycled through many previous generations of stars. This rising metallicity is not just a detail, it fundamentally changes the universe's potential. A cloud rich in heavy elements can form not only stars but also rocky planets, and it possesses the complex chemistry that is a precursor to life itself. We are quite literally the beneficiaries of this ancient and ongoing enrichment, our very world built from the legacy of countless stellar lives. The iron in your blood marks a cosmic boundary line. It is the final element a star can create through the steady, life-giving fire of nuclear fusion. This process, called nucleosynthesis, is the stellar alchemy that builds the periodic table from the inside out. Deep within a star's core, immense pressure and heat force atomic nuclei to collide and stick together, forging heavier elements and releasing the energy that makes the star shine. For most of its life, a star is a hydrogen to helium factory, but as it ages and its core contracts, the temperature soars even higher, allowing it to begin fusing that helium into carbon. In stars like our Sun, the process stops there, but in more massive stars, the fusion chain continues, creating neon, oxygen, and silicon in successive shells, like the layers of an onion. Each new fusion stage burns hotter and faster than the last. The creation of silicon, which fuses into iron, might last only a single day in a star's multi-million-year life. And iron is where the fire dies. Fusing iron does not release energy, it consumes it. The star's central engine sputters and fails. This sudden loss of outward pressure triggers the core's catastrophic collapse and the ensuing supernova explosion. It is in that unimaginable violence, in the furious seconds of the blast itself, that the heaviest elements are born. Processes like rapid neutron capture force nuclei to grab countless neutrons in an instant, creating elements like gold, silver, and uranium before they are violently scattered into the void. Every heavy atom in your body, from the calcium in your bones to the iodine in your thyroid, was forged in one of two cosmic crucibles, either in the final moments of a massive star's life or in the even more extreme conditions of colliding neutron stars. We are not just living in the universe, we are literal pieces of it, our very composition a living record of ancient stellar explosions. The tremendous energy of a supernova explosion sends a supersonic shock wave racing through the surrounding cosmic environment. This is not a gentle ripple but a titanic wall of compressed gas and radiation, moving at millions of miles per hour. As this expanding front plows into the quiet clouds of the interstellar medium, it acts like a cosmic snowplow, sweeping up vast quantities of gas and dust into an incredibly dense, cold shell. This shell is no longer a stable, drifting cloud. It is a structure under immense pressure, both from the shock wave pushing it from behind and its own rapidly increasing mass. The delicate balance that once prevented collapse is shattered. Under the relentless crush of its own gravity, this massive shell begins to buckle and fragment. These fragments, each one a dense, dark knot of potential, are the seeds of new solar systems. When a fragment reaches a critical threshold of density and mass, its inward pull becomes irresistible. It collapses, spinning faster and heating up until nuclear fusion ignites in its core, and a new star is born. This process, known as triggered star formation, creates entire families of stars, clusters, and associations, all linked by a shared heritage. They are siblings born from the same catastrophic event that marked the end of their predecessor. The magnificent Orion Nebula, a stellar nursery visible to the naked eye, provides a stunning glimpse of this cycle in action. The brilliant, hot young stars illuminating its glowing gas are likely the direct result of shock waves from ancient supernova that compressed the cloud eons ago. One generation's violent end directly sculpted the cradle for the next, a beautiful and continuous feedback loop written across the galaxy. A star's influence on its environment is not confined to its spectacular birth or its dramatic death. Throughout its entire life, a star breathes out into the cosmos. This steady exhalation is the stellar wind, a continuous stream of charged particles flowing from its surface into the void. Our own sun produces such a wind, a gentle but persistent solar breeze that shapes our entire heliosphere and creates the beautiful auroras at our poles. For a star like the Sun, this mass loss is minimal over its long lifespan, but for the true giants of the stellar world, the massive, brilliantly hot stars, the story is radically different. Their immense radiation drives winds of unbelievable ferocity, hurricane-like outflows that can tear away a star's own atmosphere. Over its short, furious life, such a star can lose an amount of material equal to many times the mass of our entire solar system, all through this relentless, invisible breath. This process of mass loss becomes a powerful crescendo as a star approaches its end. In its final phases, a star like our Sun will experience what astronomers call a superwind. This is the star's last great exhalation, a wind thousands of times stronger than its previous outflow. During this relatively brief period, the star can shed a substantial portion of its entire mass, gently puffing its outer layers into space to form the beautiful, intricate shells we later see as planetary nebulae. This is a critical, gentle form of recycling. While a supernova is a sudden, explosive dispersal of heavy elements, these stellar winds provide a continuous, steady supply. They carry newly forged carbon, nitrogen, and oxygen away from their parent stars and distribute them evenly throughout the surrounding interstellar medium, like a gardener carefully sowing seeds across a vast field. This gentle enrichment is essential for the galaxy's long-term evolution. It ensures that the raw materials for future worlds are not only available in the chaotic aftermath of violent explosions, but are also constantly and quietly replenished everywhere. The oxygen you just breathed was likely carried across light years by such a stellar wind, long before it was ever incorporated into our planet's atmosphere. This continuous cycle, working in concert with the catastrophic events, guarantees that star-forming regions are consistently supplied with the complex chemistry needed to build rocky planets and the molecules of life. It is a quieter, more patient form of cosmic alchemy, one that works tirelessly in the background, ensuring that the galaxy grows richer and more capable of fostering life with each passing generation. These microscopic grains of cosmic dust are the ultimate artisans of creation. They begin their existence not in the void, but in the atmospheres of dying stars. As a star like our Sun enters its final phases, its outer layers become a cosmic furnace where temperatures and pressures are just right for atoms to link together into solid particles. Tiny specks of silicate minerals similar to sand and carbon compounds begin to condense out of the gas, like soot forming in a candle flame. Stellar winds then carry this newborn dust outward, gently seeding the surrounding space. In the more violent demise of a massive star, a supernova explosion forges an even richer variety of dust, blasting these newly minted solid particles across vast distances. These minuscule grains are far more than just space dirt. They are fundamental to the galaxy's ability to give birth to new solar systems. A drifting molecular cloud filled with this dust is shielded from the harsh ultraviolet radiation that would otherwise tear its molecules apart. The dust acts as a cosmic sunscreen, creating dark, cold cocoons within the cloud where delicate molecules can survive and grow more complex. Furthermore, these dust grains are brilliant at radiating heat away. As a gas cloud cools, its internal pressure drops, allowing gravity to overcome its resistance and initiate the collapse that forms a new star. Without dust to cool the cloud, this critical step might never happen. On the surfaces of these tiny grains, the very chemistry of life can begin. Individual atoms adrift in the cloud stick to a dust particle. Sheltered on this solid stage, they can meet other atoms and undergo reactions, forming water ice and complex organic molecules. These icy, dusty grains become the building blocks of comets, which later deliver these essential ingredients to young planets. When a new star finally ignites, this dust does not vanish. It clumps together in the spinning disk surrounding the infant sun. These clumps collide and merge, growing from pebbles to boulders, and eventually into asteroids and entire planets. The very ground beneath your feet was once part of this ancient, starlight-forged dust. Every rocky world, every asteroid, every comet is a monument to these microscopic seeds, the silent carriers of stellar legacies across the eons. This chemistry of stellar graveyards is the universe's ultimate recipe for life. While the Big Bang provided the basic ingredients, hydrogen and helium, it was the lives and deaths of stars that cooked up everything else on the cosmic menu. The very elements that form the foundation of biochemistry, the carbon, nitrogen, oxygen, phosphorus, and sulfur that make up our DNA and our cells, are all stellar creations. Different types of stellar death specialize in producing different sets of elements. The violent supernova of massive stars are the primary sources for the oxygen we breathe and the calcium that builds our bones and shells. Meanwhile, a quieter type of star known as an asymptotic giant branch star acts as a specialized carbon factory. In its final stages, it floods the interstellar medium with this fundamental element of organic chemistry, the very backbone of life as we know it. This specific mix of available elements in a star-forming cloud is not a minor detail, it is a decisive factor. It directly influences the types of planets that can form around a new star. A system born from a cloud rich in silicon and iron will likely form rocky, metallic worlds. A cloud with a different balance of elements might only be able to form gaseous giants. Our own solar system is a product of this ancient enrichment. It formed from gas and dust that had been cycled through and enriched by countless generations of previous stars. This means the atoms that construct your body, the iron in your blood, the calcium in your bones, and the carbon that forms the framework of your every cell, were literally forged in stellar furnaces and scattered across the light years by stellar explosions. We are not just living in the universe, we are the universe, momentarily arranged into a form that can ponder its own spectacular origins. These triggers are the universe's way of jump-starting new life from old remains. The collision of two vast molecular clouds is a cosmic event of immense consequence. Drifting through the galaxy's spiral arms, these colossal, dark structures can cross paths, their gentle gravitational fields merging into a powerful, unified force. This collision sends immense ripples of pressure through the combined gas, a silent, slow-motion crash that compresses vast regions to the point of collapse. It is a gravitational crescendo that can birth entire star clusters at once. Another profound catalyst is the majestic spiral arm of a galaxy itself. As stars and gas clouds orbit the galactic center, they periodically pass through these regions of higher density, akin to traffic slowing and bunching up on a cosmic highway. This passage through a spiral density wave squeezes the interstellar medium, compressing clouds and initiating another wave of star formation that traces out the galaxy's luminous arms. The cycle becomes self-perpetuating through stellar feedback. The most massive of the newly formed stars, though young, are incredibly powerful. Their fierce ultraviolet radiation and violent stellar winds blast into the very cloud that created them, carving vast bubbles and sending new shock waves crashing into surrounding gas. This feedback can tear a nebula apart, but it can also trigger the next round of star birth along its compressed edges, a chain reaction of creation. As a giant cloud collapses under one of these triggers, it never falls in as a single object. It shatters. The cloud breaks apart into a hierarchy of smaller, denser clumps, each destined to become its own stellar system. The most massive stars ignite only in the very heart of the collapse, in the densest knots where material rains down the fastest. This is why we often see brilliant, short-lived blue giants surrounded by families of smaller, longer-lived siblings. And the entire process is supercharged by the enriched material from previous stellar generations. The metals and dust ejected from stellar graveyards are not passive ingredients. They act as a cosmic coolant, allowing the collapsing cloud to shed heat more efficiently. This cooling enables the gas to fragment into finer and more numerous clumps, leading to a richer harvest of stars, including smaller, more stable stars like our own Sun. The result is a profound and intimate connection across eons. The violent death of one generation of stars in a supernova, or the gentle exhale of a planetary nebula, does not just provide the bricks and mortar for the next. It actively prepares the site and lays the foundation, ensuring that the galaxy's great stellar nurseries often rise directly from its most ancient graveyards. A star's mass is the ultimate clock, ticking down the seconds of its existence and setting the schedule for cosmic renewal. For the true giants of the stellar world, those born with many times the mass of our Sun, the clock races forward at a breathtaking pace. These brilliant blue-white stars burn through their nuclear fuel in a celestial frenzy, living for only a few million years before they exhaust their resources. Their end is a spectacular supernova, a sudden, violent donation of newly forged heavy elements to the galactic reservoir. This rapid cycle means that within just a few million years of a star cluster's birth, the most massive stars have already died and seeded the surrounding cloud with the oxygen, neon, and silicon necessary for rocky worlds to one day form. Our own Sun represents the patient middle class of stars. It has burned steadily for nearly 5 billion years and will continue for about another 5 billion before it swells into a red giant and ultimately sheds its outer layers as a planetary nebula. This entire process, from birth to final contribution, spans roughly 10 billion years. While this seems an eternity to us, on a galactic timescale, it is a measured, deliberate pace of enrichment. The gentle winds and eventual nebula from stars like our Sun are the primary sources of carbon and nitrogen, the essential elements of life, released in a slow, steady infusion rather than a sudden, explosive blast. Then there are the universe's slowest burners, the diminutive red dwarf stars. With masses a fraction of our sun's, they are models of stellar frugality, conserving their hydrogen fuel so efficiently that their projected lifespans stretch for trillions of years. This is so long that the universe itself is not yet old enough for a single red dwarf to have reached the end of its life. Most of these faint, long-lived stars are still in their infancy, holding onto their material and waiting for a future so distant it is almost impossible to conceive. Their eventual, quiet ends will one day contribute their own unique mix of elements to a far future galaxy. This staggered timeline is the universe's master plan for sustainable creation. It is not a single, one-time event, but a continuous, overlapping cycle. The quick, explosive deaths of massive stars provide the initial, heavy elements needed to build the first rocky planets. The slower, more gentle contributions from sun-like stars then pepper the galaxy with the carbon-based chemistry that is the precursor to life. And the trillions of years-long lives of the smallest stars act as a long-term savings account, locking away material that will one day enrich eras of star formation we cannot yet imagine. Each stellar generation builds directly upon the chemical legacy of the last, a cosmic inheritance that grows richer and more complex with every passing billion years. Our solar system and everything in it is a product of this exquisite multi-generational timing. These galactic graveyards reveal their secrets only when we learn to see in every kind of light. Our eyes perceive just a sliver of the true cosmic drama, a narrow band of visible color we call the optical spectrum. With optical telescopes, we capture the breathtaking beauty of planetary nebulae, their intricate shapes glowing in vivid greens and reds, and we trace the delicate, fiery filaments of ancient supernova remnants. But to understand the full story, we must look deeper beyond what our eyes can naturally see. When we point infrared telescopes toward these same regions, an invisible world materializes. Infrared light slips effortlessly through the veils of cosmic dust that block visible light, allowing us to peer directly into the heart of stellar nurseries. We can observe the warm glow of dust grains themselves and study the final, cool stages of stars as they gently return their substance to the galaxy. This is like seeing the skeletal framework of a construction site hidden behind beautiful but opaque walls. To witness the most violent processes, we turn to X-ray telescopes. These instruments detect the high-energy radiation emitted by gas heated to millions of degrees. They show us the searing shock fronts of supernova remnants as they slam into the interstellar medium and reveal the intensely hot, whirling accretion disks of material spiraling into black holes and neutron stars. Meanwhile, radio telescopes listen to the quiet, cold universe. They trace the vast, dark clouds of neutral hydrogen gas, the primary raw material for new stars, and they detect the faint radio whispers of specific molecules, the complex organic compounds forming on dust grains in deep space. Each type of observation is a single chapter of a much larger book. Only by combining them all can we read the complete narrative of cosmic death and rebirth. This multi-wavelength approach is what truly allows us to witness the entire cycle, from a star's final breath to the first flicker of its successor. Our view from the Earth's surface, however, is fundamentally limited. Our protective atmosphere blocks many of these crucial wavelengths, leaving us partially blind to the universe's full spectrum. This is why space-based observatories have been so revolutionary. The Hubble Space Telescope, with its crystal-clear vision in visible and ultraviolet light, has provided stunning, iconic images that have defined these cosmic landscapes in our minds. The Chandra X-ray Observatory acts as our eyes on the high-energy universe, mapping the immensely hot and violent components of these graveyards. and the James Webb Space Telescope, with its profound sensitivity to infrared light, is now pulling back the final curtains. It peers into the deepest, dustiest cocoons to show us stars and planetary systems in their very earliest stages of formation, directly connecting the recycled remains of the old with the birth of the new. These tools, working in concert, transform these distant, ethereal shapes into dynamic, three-dimensional laboratories. They allow us to measure temperatures, densities, chemical compositions, and velocities, turning beautiful cosmic ghosts into data points that tell the story of our own origins. We are not just looking at pretty pictures, we are assembling the evidence of a continuous, galaxy-wide recycling process, one that has been running for billions of years and in which we ourselves are active participants. Our solar system carries within it a chemical memory of its own violent and beautiful conception. We can read this history not in ancient rocks, but in the most primitive objects that fall from our skies, meteorites. Within a special class known as carbonaceous chondrites, scientists have found tiny, ancient time capsules called Presolar grains. These microscopic specks of dust are older than our Sun itself. They are literal pieces of other stars, forged in their atmospheres and ejected into space long before our solar system even began to coalesce. Each grain is a silent witness from a different stellar origin. By analyzing their unique chemical fingerprints, their isotopic signatures, researchers can trace them back to their specific stellar parents. Some grains carry the distinct mark of red giants, others the unmistakable imprint of supernova explosions, and still others the unique signature of stars known as asymptotic giant branch stars. This is the ultimate forensic evidence, proving our solar system was built from a rich mixture of recycled stellar remains. But the story gets even more specific. The early solar system was also seeded with short-lived radioactive isotopes, forms of elements that decay too quickly to have existed for long on their own. Their presence in the oldest meteorites is like finding a still, warm ember at the scene of a fire. It points to a recent cataclysmic event that injected these fresh radioactive elements directly into our natal cloud. The most likely culprit was a nearby supernova, whose colossal shock wave not only delivered these new ingredients, but also provided the final, triggering compression that caused our local pocket of gas and dust to collapse into the Sun and its surrounding planetary disk. So the very existence of our solar system may be the direct result of a stellar death occurring right next door. Every atom in your body, the oxygen in your lungs, the carbon in your cells, and the iron in your blood was processed through at least one previous star. We are not just inhabitants of the cosmos, we are its archived history, a living testament to the endless cycle of galactic death and rebirth. Our very address in the Milky Way may be the most critical factor for our existence. Astronomers call this the galactic habitable zone, a theoretical band within a galaxy where the conditions are just right for complex life to arise. It is not about a single star's warmth, but about the galaxy's overall architecture and history. This zone represents a delicate balance between two fundamental cosmic requirements. The first is the need for enough heavy elements, what astronomers call metallicity, to form rocky planets like our own Earth. These elements are forged exclusively in stellar furnaces and scattered by stellar deaths, meaning a planetary system must form in a region that has been sufficiently enriched by previous generations of stars. The second requirement is safety. A world must be shielded from the galaxy's frequent cataclysms. Areas too close to the bustling galactic center are perilous neighborhoods. There, stars are packed tightly together, and the risk of a nearby supernova or a close encounter with another star disrupting a planetary system is dramatically higher. Intense radiation from the central supermassive black hole and countless young, massive stars could also sterilize the surfaces of any budding worlds. Yet, venturing too far out into the galactic hinterlands presents a different problem. The sparse stellar populations in the outer reaches have not been seeded with enough heavy elements from stellar graveyards. There you might find gas giants, but the building blocks for dense terrestrial planets would be in short supply. Our solar system appears to occupy a sweet spot. We are situated in a relatively quiet suburb, about halfway out along one of the Milky Way's spiral arms. This location allowed our system to form from gas and dust that had been enriched by many stellar generations, providing the iron, silicon, and oxygen for our world, while keeping us at a safe distance from the galaxy's most violent and crowded regions. This cosmic positioning suggests that the potential for life is not evenly distributed across a galaxy. It is a direct consequence of the galaxy's own life cycle, where the fertile grounds for biology are cultivated over billions of years by the very processes of stellar death and rebirth that make such worlds possible in the first place. The clock is ticking for our own star, a future resident of the galactic graveyard it has helped to populate. In roughly 5 billion years, the Sun's steady fusion of hydrogen will falter as its core fuel runs low. This will trigger a profound transformation, beginning its final act. The Sun will swell dramatically, reaching out past the orbit of Earth, becoming a red giant. Its intense heat will utterly transform the inner solar system, ending our planet's story long before the star's final curtain call. This is not a violent explosion, but a more gradual and majestic unfolding. After its time as a red giant, the Sun will gently shed its outer layers into the void, creating a vast, luminous shroud around its core, a planetary nebula visible from far across the galaxy. For thousands of years, this beautiful, glowing cloud will be the Sun's legacy, a final monument to its long life of steady light. What remains after this beautiful display fades is the star's hidden heart. The exposed core, no longer powered by fusion, will contract into a white dwarf, an Earth-sized sphere of incredibly dense matter. It will be a stellar ember, glowing with residual heat for billions of years as it slowly cools toward darkness. This white dwarf is the final, enduring tombstone for our solar system. Yet the material expelled into space tells a different story, one of continuation. That nebula cloud is rich with elements the Sun cooked during its lifetime. A gift of carbon, oxygen, and nitrogen it returns to the cosmic reservoir. These are the very elements that form the backbone of life on our world, now being gifted back to the galaxy. This ejected material will not remain in a single, beautiful cloud forever. It will drift, gradually mixing with other stellar debris and primordial gas in our corner of the Milky Way. Over millions of years, these atoms will become part of a larger, colder molecular cloud. Within that cloud, the Sun's specific contribution of carbon and oxygen will one day be incorporated into a new generation of stars and the planetary systems that form around them. The iron from our world's core, the oxygen from our atmosphere, and the carbon that once was part of every living thing here could find new homes in distant future worlds. So while our local solar system will be gone, the Sun's physical substance will live on. Its death is not an end, but a vital contribution to the galaxy's ongoing cycle, a final act of cosmic recycling that ensures its legacy is woven into the fabric of whatever comes next. This ongoing enrichment is the galaxy's own story of growing up, written in the chemical signatures of its stars. We can trace this history by studying the metal content, or metallicity, of stars of different ages. The very oldest stars we can observe, found in the outer halo of our galaxy or in ancient globular clusters, are strikingly metal poor. Their atmospheres contain only the faintest traces of elements heavier than hydrogen and helium. These are the venerable population II stars, the second generation. They formed from gas that had been seeded by just one prior round of stellar explosions. Their existence points back to a truly lost generation, the very first stars, known as Population 3. These pioneers were born from the pristine hydrogen and helium left by the Big Bang. Without any heavier elements to help them cool and fragment, they were likely behemoths, dozens or even hundreds of times more massive than our Sun. They lived fast and died young in colossal supernova, and in their brief, brilliant lives, they performed the universe's first alchemy, forging the first carbon, oxygen, and iron and scattering it into the void. That first pollution was the crucial first step, the moment the galaxy's potential for complexity began. Every generation that followed built upon this foundation. As the interstellar medium grew richer with each cycle of stellar death and rebirth, the star formation process itself changed. The presence of metals and dust allowed giant gas clouds to cool more efficiently and fragment into smaller, more stable clumps. This is why later generations, like our own Sun, which is a population 1 star, are more common and less massive. This rising metallicity did not just change the stars, it fundamentally altered the kinds of planets that could form around them. A protoplanetary disk rich in silicon, iron, and carbon could coalesce into dense, rocky worlds. A disk made only of hydrogen and helium could only form gas giants. The very existence of our Earth, with its iron core and rocky mantle, is a direct consequence of this multi-generational chemical enrichment. The calcium in your bones and the oxygen in your lungs are the legacy of countless stellar ancestors, whose lives and deaths over billions of years gradually transformed a simple, primordial universe into one capable of crafting a world that can sustain life. These dark nebulae are the galaxy's deep freezes, immense reservoirs of cold gas and dust so thick they blot out the light of the stars behind them. What appears to our eyes as a simple patch of blackness is in fact a cosmic womb, a molecular cloud where the temperature hovers just a dozen degrees above absolute zero. In this profound, cold, and deep shadow, the chaotic energy of the wider galaxy is subdued, allowing gravity to begin its patient, irresistible work. The dust itself is the unsung hero of this quiet drama. These microscopic grains, forged in earlier stellar deaths, form a protective shield against the harsh ultraviolet radiation that would otherwise tear molecules apart. Sheltered within this cosmic cocoon, simple atoms can meet and link together. It is on the surfaces of these dust grains that two hydrogen atoms can find one another and form molecular hydrogen, the primary fuel for the next generation of stars. This delicate, cold environment allows for the formation of ever more complex molecules, including the precursors to the chemistry of life. The famous Horsehead Nebula, a silhouette of dark dust against a glowing background, offers a stunning portrait of this early stage. It is not an empty void, but a dense, structured cloud, a nursery in waiting where the raw materials for entire solar systems are slowly, silently accumulating. Here, the galaxy's grand cycle of death and rebirth finds its most patient phase, a long, quiet gestation in the dark before the eventual ignition of new light. But these cosmic processes are guided by an invisible hand. Throughout the vast expanses between the stars, powerful magnetic fields weave an intricate, unseen architecture. These forces are not mere background features, they are active participants in the cycle of stellar death and rebirth, shaping the flow of matter across the galaxy. Within a dark molecular cloud, gravity may be eager to pull everything together, but magnetic fields provide a crucial counterbalance. They act like a cosmic support structure, propping up vast regions of gas and dust and significantly slowing their collapse. This magnetic resistance is not a permanent barrier but a regulatory mechanism. It prevents clouds from collapsing too quickly and chaotically, allowing material to be channeled along the invisible field lines. This channeling funnels gas into specific streams and sheets, directly influencing the final architecture of the stellar nursery that forms. As a cloud core finally contracts under gravity's pull, these embedded magnetic fields also govern its spin. They help carry away excess rotational energy, allowing the infant protostar to form without spinning itself apart. The entire structure of a forming solar system, from the size of its central star to the orientation of its eventual planetary disk, can be shaped by these fundamental, invisible forces. The influence of magnetic fields only intensifies in the chaos of a stellar graveyard. Inside a supernova remnant, the expanding shock wave and turbulent debris become a natural particle accelerator. The tangled magnetic fields within the remnant trap charged particles, whipping them back and forth with incredible force until they are hurled outward at nearly the speed of light. These particles become cosmic rays which flood the galaxy and contribute to the very background radiation that can influence the chemistry within other star-forming clouds. How can we possibly map something so intangible? Astronomers have a clever method. They observe the light from distant stars as it passes through clouds of interstellar dust. These non-spherical dust grains tend to align themselves with the local magnetic field like countless tiny compasses. This alignment polarizes the starlight, imparting a specific directional preference to its waves. By measuring this polarization across the sky, we can effectively trace the structure of the magnetic fields threading the darkness, revealing the hidden scaffolding upon which new stars are built. From resisting collapse to guiding accretion and accelerating particles, magnetic fields are the silent conductors of the cosmic orchestra. They ensure that the recycling of stellar material is not a random, chaotic scramble, but an organized and structured transformation, proving that even in the apparent emptiness of space, invisible forces are perpetually at work, sculpting the next chapter of galactic life. The invisible architecture of our solar system was written long before the sun's first light. When a new star ignites within an enriched cloud of gas and dust, its birth is not an isolated event but the beginning of a magnificent construction project. The same spin that defines the star's rotation flattens the surrounding material into a vast, spinning disk, a protoplanetary disk that becomes the workshop for building planets. Within this disk, the microscopic dust grains born in earlier stellar deaths finally find their purpose. They are the seeds of worlds, the fundamental building blocks that begin to collide and stick together in a gentle cosmic dance. At first, these are mere specks, but over thousands of years they grow into pebbles, then boulders, and eventually into mountain-sized bodies called planetesimals. This is the critical transition where gravity begins to take a direct hand, pulling these planetesimals together in a series of increasingly violent collisions that forge the cores of future planets. The entire character of the resulting solar system is imprinted by the composition of its original cloud, a disk born from material rich in metals, the elements heavier than hydrogen and helium, possesses the raw ingredients to form dense, rocky worlds. Silicon and iron can coalesce into metallic cores and rocky mantles, creating terrestrial planets like Earth, Venus, and Mars. In contrast, a disk that is metal-poor may lack the solid seeds necessary to build large rocky cores quickly. In such a system, the vast reservoirs of hydrogen and helium gas remain available longer, allowing massive gas giants to form directly, often orbiting close to their star. Our own solar system displays a remarkable mixed architecture that tells a specific story about its origins. The inner solar system, with its 4 terrestrial planets, formed in a hotter region where only materials with high melting points, like metals and silicates, could remain solid. Farther out, beyond the frost line, water and other volatiles could exist as ice, providing much more solid material for planetesimals to rapidly grow into the massive cores that then accreted enormous gaseous envelopes, becoming the giants Jupiter and Saturn. This entire layout, from the rocky world beneath our feet to the gaseous giants in the outer darkness, is a direct reflection of the specific conditions and chemical makeup of the molecular cloud that collapsed 4.6 billion years ago. The legacy of those long-dead stars did not just provide the atoms, it dictated the very blueprint, determining what kinds of worlds could be built and, ultimately, which of those worlds might one day become a suitable home for life. The universe's great cycle of stellar renewal is not a permanent fixture. It has a lifespan of its own, a grand trajectory that will one day lead to a very different cosmos. Billions of years from now, the vibrant stellar nurseries we see today will grow quiet. The rate of star formation across the universe actually peaked long ago and has been on a slow, steady decline ever since. Galaxies are gradually using up their finite supply of raw hydrogen gas, the essential fuel for new suns. As this fuel is locked away into long-lived stars and stellar remnants, the great engines of creation begin to sputter. In this far future, the galactic graveyards will become the dominant feature. The balance will shift from bustling nurseries to quiet necropolises, where the population of white dwarfs, neutron stars, and black holes will vastly outnumber the shining stars. The interstellar medium itself will continue its chemical evolution, growing ever richer in heavy elements as each successive stellar generation completes its life cycle. This rising metallicity could fundamentally alter the types of stars that are born. Future stellar nurseries, should any still ignite, might form stars that are different from any we see today, perhaps more prone to developing powerful stellar winds or evolving in novel ways. Yet even this enrichment has a final limit. On timescales so vast they defy human comprehension, the great recycling program will eventually run down. The raw gas will be too depleted, the remaining clouds too diffuse to collapse. Star formation will cease entirely, leaving galaxies as collections of fading embers. These will be the final inhabitants, the stellar remnants and the cold, failed stars known as brown dwarfs, all orbiting in an ever-darkening silence. The brilliant, dynamic era of cosmic rebirth, the very epoch that gave rise to our world, will have become a closed chapter in the history of the universe. The view from beyond our own galaxy reveals a universe of astonishing variety in its cycles of creation. Looking at stellar graveyards in other island universes shows us that the recycling process is universal, yet deeply influenced by a galaxy's specific environment and history. Take the starburst galaxy, for instance, a celestial frenzy of star formation. Here, the sheer density of massive, short-lived stars means supernovae detonate with startling frequency, like a chain of cosmic firecrackers. These violent deaths churn the galactic environment, flooding it with newly forged heavy elements and carving out vast bubbles of hot, ionized gas. The entire galaxy becomes a single, intense workshop, where stellar life and death accelerate at a breathtaking pace, creating a landscape rich with the raw materials for new solar systems almost instantaneously on cosmic timescales. In stark contrast, consider the majestic elliptical galaxies. These ancient, rounded giants are the quiet retirement communities of the cosmos. They formed the bulk of their stars in a furious burst of activity billions of years ago and have seen little new star formation since. Their stellar graveyards are therefore populated by the long-cooled remnants of that initial, ancient generation. White dwarfs and neutron stars from a bygone era drift through these galaxies, and the interstellar medium is correspondingly calm and enriched with a specific, older blend of elements. The chemical signature of an elliptical galaxy tells a story of a massive, early enrichment event, followed by eons of relative quiet, a very different evolutionary path from the continuous recycling seen in spiral galaxies like our own. Even our closest galactic neighbors, the Large and Small Magellanic Clouds, tell a compelling story of environmental influence. These irregular dwarf galaxies have a much lower abundance of heavy elements compared to the Milky Way, a state we call low metallicity. This fundamental difference in composition directly shapes the stars that form there. Without as much metal-rich dust to help clouds cool and fragment, star formation can take on a different character, and the stellar populations that emerge have distinct life cycles. Planetary systems forming in such an environment would be built from a more primordial mix of materials, potentially leading to worlds very different from our own. The presence of spectacular nebulae like the Tarantula Nebula in the Large Magellanic Cloud, a colossal star-forming region, proves that vibrant stellar nurseries can thrive even in these metal-poor conditions, but the planets they build will carry a unique chemical fingerprint. These extragalactic perspectives are crucial. They allow us to test our models of stellar evolution and cosmic recycling against a much wider array of conditions. Is the process that forged our solar system the same everywhere, or does a galaxy's mass, shape, and history dictate its own unique rhythm of death and rebirth? By comparing the graveyards and nurseries across the cosmos, we begin to see our own place in a much larger tapestry. Our Milky Way's specific cycle of stellar life and death is not the only way a galaxy can exist, but simply one variation on a magnificent universal theme, a theme that writes the history of cosmic material across the vast expanses of space and time. That iron in your blood marks a direct link to a star that died before our world even existed. The oxygen filling your lungs right now was once the breath of a red giant, exhaled into the void millennia ago. We are not simply living in this universe, we are literal pieces of it, assembled into a form that can look back and wonder at its own origins. Every single one of us is a walking, talking collection of ancient stardust. The carbon that forms the framework of your every cell, the nitrogen that is essential to your DNA, the phosphorus that fuels your energy, all of these were forged in stellar furnaces and scattered by celestial explosions. This material journeyed for billions of years across the light years, a cosmic voyage of unimaginable scale, before finally settling into the particular cloud that would one day coalesce into our sun and its planets. The very existence of our bodies and the complex chemistry that allows us to live was only possible because the galaxy grew up. The first stars after the Big Bang were pure hydrogen and helium. They lived and died, and in their passing they seeded the cosmos with the first heavy elements. The next generation built upon that foundation, adding more complexity to the mix. It took this long succession of stellar lives and deaths, this gradual enrichment over eons, to create a galactic environment rich enough in carbon, oxygen, and nitrogen to allow for the chemistry of life to even begin. So when you feel the wind on your skin or taste the rain, you are interacting with gifts from stars that shone in the deep past. This cosmic heritage transforms our perspective. We are not separate from the universe, observing it from a distance. We are one of its most intimate and recent expressions, a temporary gathering of atoms that have lived many previous lives. The calcium that strengthens your bones may have once been part of a supernova's expanding shell. The gold in a cherished piece of jewelry was likely born in the violent collision of two neutron stars. We are the universe momentarily conscious of itself. This realization invites a profound sense of connection and responsibility. We are the temporary custodians of this ancient stellar material. For a brief moment in cosmic time, these atoms are arranged as us, capable of thought, emotion, and wonder. And one day, long from now, they will return to the great cycle, flowing back into the interstellar medium to become part of new worlds, new stars, and perhaps new life. Our physical connection to the cosmos is not a metaphor. It is the most fundamental truth of our existence. This fundamental research into the depths of stars quietly powers some of our most vital earthly technologies. The quest to peer into the hearts of supernova remnants drove the development of incredibly sensitive X-ray telescopes. The engineering challenges of capturing these high-energy photons from space directly influenced the refinement of medical imaging devices. The result is the advanced X-ray machines and MRI scanners found in hospitals today, offering doctors a non-invasive view inside the human body with a clarity born from our need to see across the cosmos. The intricate detectors first built to map the aftermath of stellar explosions now help diagnose illnesses and save lives, a profound return on our investment in cosmic curiosity. Similarly, the titanic shock waves that race through expanding supernova remnants are natural laboratories for studying extreme physics. Scientists modeling these supersonic fronts have gained critical insights into fluid dynamics and plasma behavior. This knowledge directly translates into designing safer and more efficient supersonic aircraft and spacecraft, especially vehicles that must withstand the intense heat and pressure of atmospheric re-entry. The same forces that sculpt nebulae now help us navigate our own planet's thin skin of air. Even the invisible rain of cosmic rays, atomic fragments accelerated by stellar remnants, has practical importance. Monitoring these high-energy particles is crucial for understanding background radiation levels, which informs safety protocols in the nuclear power industry and for astronauts living aboard the International Space Station. It also helps us protect sensitive satellite electronics from being disrupted by these subatomic bullets from deep space. Perhaps the most widespread application lies in the realm of time itself. The very elements forged in stellar explosions provide the clocks we use to measure Earth's history. Radioactive isotopes like uranium-238, created in supernova, decay at a known steady rate. By measuring the ratio of this isotope to its stable daughter product, lead, geologists can date the formation of our planet's oldest rocks. This technique, radiometric dating, is a direct gift from stellar nucleosynthesis, allowing us to read the billion-year-old story of our own world. These are not mere coincidences, but a testament to the unity of physical law. The same principles that govern a star's death also operate here on Earth, and by reaching for the stars to answer our deepest questions, we often find the tools to build a better future right at home. These ancient stories were humanity's first theories of cosmic evolution. Long before telescopes or spectrometers, people looked up at the same night sky we study today and wove narratives to explain its mysteries. They saw not random points of light, but a celestial drama filled with gods, heroes, and monsters, whose lives in the heavens mirrored the cycles of life and death here on Earth. When a new star suddenly blazed into view where none had been before, cultures across the globe recorded these events as profound omens. The sudden appearance of what we now know was a supernova in the year 1054 was interpreted in vastly different ways. Chinese astronomers meticulously documented it as a guest star, a temporary celestial visitor. Half a world away, ancestral Pueblones in the American Southwest may have captured its brilliant light in a rock carving, while other cultures might have seen it as the birth of a deity or the passing of a great chief. These interpretations were more than just superstition. They were an attempt to place a sudden, violent, and brilliant change in the cosmos into a narrative that made sense to them, a story where the sky was alive and its events held deep meaning for life on the ground. The recurring myth of the phoenix provides a stunning parallel to the science we understand today. This legendary bird, present in both Greek and Egyptian traditions, cyclically dies in a burst of flame only to be reborn anew from its own ashes. Is this not a powerful, intuitive metaphor for a massive star ending its life in a supernova inferno, whose expelled remains then seed the birth of future stars and planets? Similar concepts of cyclical destruction and regeneration appear in Hindu cosmology with its repeating cycles of creation and dissolution, and in the Norse myth of Ragnarok, a great battle that ends the world but is followed by its rebirth, fertile and green. Modern astrophysics has replaced these mythic frameworks with an evidence-based model, one built on mathematics, observation, and the laws of physics. We no longer see the hand of a deity directly placing a new star in the sky, but we can trace the nuclear processes that forge the elements and the gravitational forces that sculpt nebulae. Yet the core narrative, the fundamental pattern that death is not a final end but a transformation that enables new beginnings, remains powerfully intact. This continuity across millennia and cultures suggests that this pattern resonates with something deep within the human psyche. We see the same cycle in the passing of the seasons, in the decay of a fallen log that nourishes new growth, and now we have confirmed it in the very stars above. Our scientific understanding has not diminished the poetry of the cosmos. It has given us a new, even more profound language with which to appreciate our intimate and enduring connection to this grand, universal cycle. Yet for all we have learned, the inner workings of these galactic recycling centers remain partially veiled. Astronomers are still untangling the precise physics of how a supernova's shock wave, a wall of pure energy, can so effectively compress a gas cloud into a new star. We understand the broad strokes, but the fine details of this triggering process and its true efficiency across different environments are active puzzles. The galactic contribution of different stellar deaths is also under scrutiny. While we know massive stars produce oxygen and supernova forge iron, the origins of certain rarer elements are less clear. How much do the gentle winds from aging giants contribute compared to the violent mergers of neutron stars? The complex dance of binary star systems adds another layer. When two stars orbit one another, they can exchange material, alter each other's life cycles, and create unique pathways for element production that single stars cannot replicate. This intricate interplay is a major frontier in understanding the chemical diversity we see across the galaxy. Perhaps the most profound question lies closer to home. We know planets form from enriched disks of dust and gas, but why is the outcome so spectacularly varied? Why do some stars host compact, rocky worlds while others have bloated gas giants orbiting perilously close? The link between a protoplanetary disk's specific chemical makeup and the final architecture of its planetary system is a key mystery. The answers to these puzzles are coming into focus with a new generation of observatories. The James Webb Space Telescope, with its infrared eyes, is peering into the hearts of stellar nurseries and the dusty shrouds of dying stars, directly tracing the flow of organic molecules and newly forged elements. Meanwhile, the next wave of enormous ground-based telescopes will dissect the light from distant stellar graveyards with unparalleled precision, measuring their chemical fingerprints in exquisite detail. Each unanswered question is not a roadblock, but a signpost pointing toward a deeper truth, guiding our exploration of how cosmic death so reliably and so beautifully fuels the rebirth of worlds. Our journey through the galactic graveyards reveals a universe governed by magnificent cycles, where endings are consistently woven into new beginnings on a cosmic scale. We have witnessed how the explosive finales of supernova and the gentle exhalations of planetary nebulae perform the same essential duty. They transform the sparse interstellar medium into a rich chemical broth, seeding it with the very elements forged in stellar hearts. This continuous process of cosmic recycling connects us directly to the stars in the most intimate way imaginable. Every atom of oxygen in a deep breath, every particle of iron coursing through your veins was once part of a star that lived and died long before our sun was even a glimmer in the galaxy. We are not just inhabitants of the universe, we are its archived history, a temporary gathering of ancient stardust now capable of looking back and understanding its own origins. As we consider the far future, both of our own civilization and of the cosmos itself, this perspective invites a profound sense of place. We are fleeting participants in an eternal process of transformation, a single note in a symphony that has been playing for billions of years. This knowledge that we are the universe contemplating itself stands as one of the most beautiful and humbling gifts of modern science. It redefines our connection to the cosmos, not as distant observers, but as active, conscious expressions of its ongoing creative story. If this journey through the cosmic cycle of death and rebirth has reshaped how you see your place in the universe, please share this video with someone else who might find wonder in these astronomical stories. Subscribing to our channel ensures you do not miss our next explorations into the phenomena that shape our cosmos, from the birth of stars to the mysteries of dark matter. We are genuinely curious to hear which part of this stellar story resonated most with you. Was it the violent beauty of supernova, the patient artistry of planetary nebulae, or the profound idea that we are all made of stardust? Let us know your thoughts in the comments. Your participation and questions fuel our mission to create more content that illuminates the incredible processes weaving through our universe. And the next time you find yourself beneath a clear night sky, take a moment to truly look up. See it not as a static picture, but as a living, breathing narrative, a grand, ongoing story of cosmic endings and beginnings to which we all intimately